Okay, great. And yeah, there should be plenty of time for discussion at the end. So if you have a clarifying question, yeah, go ahead and jump in. But if it's a longer kind of discussion-y question, we can definitely do that at the end. Okay. So many of us, sorry, I'm trying to just like arrange my windows here. Okay, are familiar with these kind of semantic space models, going all the way back to latent semantic analysis. And now they're used a lot also in machine learning. And so you can see here, this is a one-dimensional arrangement of several types of people, and the one dimension is age. You can expand this into, for example, a two-dimensional arrangement, and this actually gives you a lot of information. So in addition to being able to see the age, we have added a dimension of gender, and now we can calculate the distances between any point and any other point, which gives us a distance which is linearly related to well, no, it's not linearly related, but it's related to similarity. These values on the dimensions can be captured, formally with numbers like this, and sometimes you see them visualized in a way like this. So any questions so far? This is probably review for most people. But the question is, and we've seen using these kind of word embeddings, space models, some types of analogy may be possible, at least, according to this word2vec and TensorFlow implementation, and this got a lot of attention a couple of years ago. And here in the seminar, we've actually even had a presentation on BART, which again tries to put relational concepts into this sort of feature vector framework. I'm going to be completely honest, I did not follow all the details of the BART talks. I think we might have had two, one from Holyoke and one from Lou. So when we get to the end, if somebody wants to help explain it to me, I think that would be great. I think that would be a helpful part of the discussion. But for me, my questions come from thinking about cognitive science and teaching. So if these vector space models did reflect something about human cognition, what would it mean for teaching relational concepts? Because as I'm sure we're all very familiar with by now, relational concepts are critical in STEM. I mean, math is basically just all relational concepts, right? From a computational perspective, you would expect that the most varied set of examples should be the most helpful, and I'll go into why a little bit more. But when you look at actual human data and actual things that seem to work with actual people, there's this idea of progressive alignment, which is instead of using as disparate examples as possible, slowly moving away in surface similarity. Any questions so far? I'm not sure I can see the chat window, so let me know.
Yeah, we'll keep an eye on the chat and hands.
Okay.
Yeah.
Okay. Great. Okay. So this is just a walkthrough of what this kind of model might look like. So here's just object properties for an entity. The entity is the triangle. It has the dimensions, you could say color, fill, and shape. And for each of these dimensions, it has a positive value. So you could think of these as like ones and zeros. The ones that are filled in are ones, and the open ones are zeros. It's kind of a dummy variable coding scheme, or in machine learning, they call it one-hot. Sounds cooler, but it's just dummy variables. Now, if you put two of these entities next to each other, you can compare their feature vectors, and you can actually make some relational, a vector about their relations, basically. And for these two, the only thing they have in common is color. So same color, but not same fill or same shape. And then we can add this, the relational features, onto the object features to get a way of representing this pair. And so, for example, if we have another pair, it has completely different object features, but it has the same relational features. And so if we're able to abstract out a relational concept, one way to model that would be as somehow putting the importance on these relational features in the vector. And so weighting them actually, and down weighting the superficial features, the surface features. Well, we think that this is what experts and novices do. Novices would say that these two go together because they're superficially similar. But the expert would say, actually, these two go together because on a deeper level, the relational concepts underlying them go together. And of course, this is from Feltovich and Shi. Sorry, I didn't have the citation at the bottom of the slide. Okay, so one way to think of this is that maybe experts are, what's different about the way experts represent their domain is that they are able to put a greater weight on the relational features and kind of ignore the superficial features. Okay. So I did a little experiment. The stimuli looked like this. So the participants would see two pairs and be asked if it was a relational match. And we had a little explanation beforehand of what do we mean by a relational match. And so in that case, it would be same shape, same color, same fill, which combination of those. So within this, for example, we have same color, but different shape and different fill. And here we have different fill, different shape, and different colors. So this one would be not a match. This was done on gorilla during COVID. The participants were undergraduates. There was no feedback given. So the stimulus base was that the pairs were made out of was like this. So they varied on all three dimensions for 3 possible values. Okay, so what we found was if the two pairs, right, the more shared object features they had, they did tend to have more people say, yes, this is a relational match. However, we also found that they would say that there's a relational match even when there wasn't. These are hits and these are false alarms. And the difference between them is actually a little bit lower at the highest number of shared features. So having more features and surface features in common makes you more likely to say it's a relational match, but even when it's not actually a relational match. So if you think about it in terms of discriminability, there's lower discriminability. We also did a similar study. This was with my colleague, Emma Lazaroff, using non-symbolic fractions. So here, these two lines form a ratio. Each pair of lines has a ratio. And they can vary in their color and also in their absolute size, as opposed to the ratio between the two lines. And we would give participants a screen like this, and they would have to answer if the one at the bottom matched the top two. Can you guys see my mouse? Okay, great. I should have asked that earlier. Excuse me. Right. So yeah, they would see kind of these two, I wouldn't call them training, but yeah, two exemplars, and then be asked if the third one matches, specifically on a relational level. We found a very similar result. The hit rate went up as there were more shared colors between the exemplars and the test item at the bottom. But the false alarms also went up, leading to slightly lower discriminability. And I also looked at this a little bit with symbolic fractions. So we had a task where we were, where the participants, and these were kids, were comparing two fractions, and they had to choose the larger of the two fractions. So it's a magnitude comparison test. And we're all familiar with the fact that it's easier to compare two fractions that have a common denominator, because then you can just compare the numerators. You can also have fraction pairs where there are no common components. Then you get this kind of situation where there's a component that's in common, but playing a different role. So here, whoops, here the 7s are both in the denominators. Here, one is in the denominator and one is in the numerator. So I call this the mismatched components. And looking at accuracy on these different type of trials, I've spread it out over the distance on the number line. So when the fractions were closer together, the mismatched components were the most difficult. So the near condition was the hardest overall, but when there's a common denominator, the accuracy level was much higher than no common denominator, and the mismatched condition where they're superficially different, superficially similar, actually makes it harder. And this was just looking at the symbolic fractions, but I also looked at the data for the cross notation condition. So this is where we had a line ratio and a symbolic fraction, or when we had two non-symbolic fractions, or a line ratio like we saw in the previous study. And again, because that kind of surface level similarity, there's only a similarity when you're comparing the symbols, right? Like if I had 2 7ths and 7 5ths in cross notation, it shouldn't make a difference. And here we see, no, it doesn't make a difference, but it makes a difference for the symbolic condition, because that's where that surface similarity comes into play. So this is basically the same as this here. So it's saying it's not anything about the magnitudes themselves making it difficult, but it's about the way they're represented. And so when you represent them as symbolic fractions, there's this confusing surface similarity. So going back to my original question, what would this mean for how we should teach? So it looks like having more surface similarity makes you more likely to align to exemplars, even if they're not actually alignable, or even if they shouldn't be aligned. So that's why the progressive alignment approach might be successful, because when you're first introducing a concept, it's easier to align to superficially similar exemplars. And as we've seen in Gentner and Hoyos, among other places, there's no value if the two examples can't actually be aligned. So if you pick two examples that are so far apart that they can't be aligned, there's no benefit, there's no learning by analogy. But in order to avoid this kind of false positive and to make sure the correct features, the relational features, are the ones being aligned, you may need to make sure you move to those less surface similar examples. And that might require more support for alignment, like gestures, language, all those things that we know support analogical reasoning. So you may have to do more work to get that alignment, but in the long run, it should be worth it, because then you should have some representation that's on the relational level, as opposed to being kind of like contaminated by the superficial similarity. This is preliminary data. The fraction study was actually not designed to answer this question. I just kind of went back and said, well, what would happen if we looked at it this way? So you can see, I don't think these results are statistically significant, although part of that might be sample size. But here's some questions for discussion. So one thing that happens is I showed this image of relational features being added to the vector, but how did they get there? How do we get dimensions or slots for relational features? And it's even kind of a question, and I think this is partly a developmental question. How do we get these slots or dimensions into our representation for new features at all? And I don't know if that's something that people have looked at either computationally or with humans. So yeah, this is kind of like, explain to me what I'm missing. If you know, please. And are these kind of semantic space models of human cognition merely convenient? Or do we think they actually reflect something about what's happening in the mind and or brain? And going back to experts, do we think that they actually do have these abstract relational features encoded, that they've created like nodes for these features? Or maybe it's just that when you're in a domain, some of the surface similarity is actually helping you. And you start to recognize maybe which surface features are helpful and your alignment is quicker that way. So again, this is kind of a question of is there generalization, or are you remembering specific examples and comparing? And I don't have a horse in this race. I would love it if there was abstraction that happened. And we know that there are clearly situations in which humans are able to abstract or generalize. I was thinking, okay, so how would you actually test this? And I just came up with this morning. You'd have to find surface atypical examples of things that matched relationally in with experts in the domain of expertise. So I think this is pretty hard, but if anybody thinks that's a good idea and wants to help, we could do the experiment. I think I may have gone a little fast, but that is the end of my talk, and I look forward to our discussion. Thank you.